Right. Thanks for having me here for another talk. So the title of my talk is Understanding and Improving Performance and Security of Modern and Emerging Computer Architectures. Before first, let me give a brief introduction about myself. So again, my name is Fan Yao. I'm assistant professor at the Department of ECE at the UCF. I joined UCF in the year 2018. Before that, I got my Ph.D. degree in computer engineering from the George Washington University. So currently, I'm leading the computer architecture and system research lab. And in our research group, our major research focus includes computer architecture, hardware and system security, cloud and energy efficient computing. And we recently have a lot of focus on security. So let me first give a brief introduction about security issues associated with computer systems nowadays. So, I mean, we know that security of a computer system is a critical concern and has been attracting a lot of attentions these days, especially for recent years, where probably for the past decades, we know that users are increasingly using and store and processing personal and private data to some kind of remote platforms such as the cloud, right? So, and it has been reported that security breaches has cost business trillions of dollars globally. And this can come from aspect from confidentiality, integrity, or availability of a system, which is generally referred to as the CIA triad. Now, what we observed recent years is that there is a major shift in terms of the security landscape of computer systems. Particularly, we observe there are a burgeoning of hardware-based attacks exploiting, let's say, the processors, right? These attacks are extremely dangerous and hard to detect as they can bypass all the existing software-based defenses that has been there and has been built over the many decades. Example of those attacks include now even famous Spectre meltdown attack. Probably you all see this in the news, over the past 3 years since this was out in 2018. So these attacks are basically the exploitation that leverages speculation, which is a performance feature in almost all modern processor to steal secrets from a victim process without directly accessing that. And it's extremely dangerous and stealthy because it can be manifest in very simple ways. For example, you look at the bottom with code example with just 2 lines of code. And from a software perspective, these are very well written code with good bound checking, things like that. But by exploiting this process vulnerability, it's actually possible that an attacker exploiting this to recover or exfiltrate all the secret data in the memory space of the victim process. So essentially, what we have, and after this discovery of Spectre meltdown attack, there has been tens or even hundreds of variants of such attack exploiting different microarchitecture component in processors. And essentially what we observe is that there's a huge security issue in terms of the foundations of computer system, which is the hardware and the computer architecture. And we know that without solving this problem, there's really no guarantee in terms of making our system secure. So now, how do we solve this problem, right? So every time when there's a big challenge, there's opportunities. So a major theme of our research group, is basically to design secure systems that are secure by design. So essentially, we believe that security should be treated as a first-class citizen in computer architecture and system design. So along towards this end, we majorly now have 3 research directions. The first one is security of modern processors, where we look at, we investigate microarchitecture side channel attack using different sources in terms of timing and power, etc. And then we try to understand what are the root causes of these side channels and what we can do to protect commodity systems from being information leakage free. And the second direction is the high performance and the secure design for future architectures, where we look at emerging architectures with, let's say, new technology, let's say the non-volatile memory as the main memory solutions, and we try to see the technique that can both improve performance and security of these systems. And lastly, we look at hardware security for machine learning. Basically, we want to understand with the existence of so many hardware-based vulnerabilities, what are the impact of those attacks to, let's say, the robust machine learning models. And in terms of machine learning domain, we care about not only DNN-based classifiers, and we also have recent focus on looking at natural language processing models, such as language models. With that, let me briefly go over each of the projects that we are currently working on, and with also a short demo about our recent published work. So the first project is we aim to investigate the performance and security issues with respect to integration of the emerging non-volatile memory in future systems. As we know that the classical memory technology has been using DRAM for many decades, but there are some issues with DRAM that is going to be extremely challenging in the future. This includes major because there's a major with the technology scaling in the recent years, we see that DRAM is facing severe issue in terms of scalability and also the power and consumption. And with that, to solve that problem, there are new techniques which we refer to as non-volatile memories. One example of those includes Intel Optane memory. So non-volatile memory is an emerging memory technology that uses different materials for memory storage, including memristors and as a phase change materials. This memory technology offers high density, high scalability, and low static power. One of the most, promising, advantages feature of that is, if you have a DRAM chip that is DRAM DIMM that is over, let's say 256 gigabytes, with the same size of NVM, the cost per gigabyte for NVM is probably going to be a few times less than DRAM, basically because of the higher density and scalability. So now, while this NVM technique seems to be very promising to be integrated as main memories, we see there are two major problems. The first problem is usually the performance of NVM in terms of read and write access is not as good as DRAM. So we need to architect high performance NVM if they are used as main memories. And another thing that is actually probably even more important is that the lessons we take from Spectre Meltdown attack is security should be considered by design rather than as afterthoughts of breaches. So what we want to know is that our existing NVM techniques secure against information leakage that we have been really burgeoning, that has been attracting a lot of attention in recent years. So with that, I want to show one demonstration of our recent work, which is published in the Micro Conference, which is the top conference in computer architecture. So in this work, we propose a mechanism to optimize performance for a specific NVM technology, which is called ReRAM, in terms of write operation. So what we figure out is that the write performance of ReRAM-based memory is the major bottleneck, could be a major bottleneck for performance because it has varying reset and write latency requirements. And our characterization-based thing shows that if you want to write to a location of the memory, and there's a memory crossbar here within ReRAM, the latency is actually requirement actually changes based on both location, the place you want to write, and also the content with the pattern you want to write, as we see in this figure. With that, so apparently there's a huge variation in terms of the required latency for the reset or the write operation. If you use the maximum with the global worst case write policy or write latency, it's going to incur huge deviation in terms of performance, right? But this is what we do in current processor, in current architectures. We use fixed latency. So in this work, we are proposing a new microarchitecture support in the processor side that enables the processor with the memory controller to leverage different and varying latency for writes based and by tracking the data content, the data pattern with this processor. So what do we propose? A letter scheme that maintains both metadata and normal data in the same memory chip. With the metadata, we are able to track the runtime data pattern of the processor of the memory in the ReRAM chip, and then use that to derive the minimally required latency for the write operation. So we demonstrate this only by simulating this only in a full system, and our result evaluation shows that our technique can actually bring tremendous performance improvement as compared to state-of-art mechanisms. So as a summary of this project, so basically this work, we show that we can significantly enhance the write performance for ReRAM, and also enable low overhead technique that can be integrated into future processors. But we don't stop, or we don't want to stop at this point. Essentially, we want to understand what is the impact of this performance optimization to security as well. So to that end, we also think that this work can serve as a working prototype for future research works on security for ReRAM devices. So currently this project is sponsored by, this actually research direction is sponsored by 2 active NSF grants. We have a couple of publications going on, and also we have 1 patent and application and several papers under submission. So let's look at now the second project is essentially this one. We focus on understanding and mitigating information leakage in modern processors. We specifically want to focus on side and covert channels. So side channel is a form of information leakage attack where you have an attacker, let's say a spy, who try to exfiltrate or infer secrets from a victim process, not by directly reading the secrets from the application, but by observing the side effects of the executions of this victim on this hardware. So essentially, the Spectre meltdown attack belongs to this category as well. But what we figure out is that there are many more microarchitecture components which might be vulnerable to this kind of exploitations, and we need to rethink architecture design based on observations. So in this project, our objective is to explore the side covert channel due to modern architecture design, and with a goal to eventually design low-cost architecture and system-level mitigation techniques. Right. Our approaches includes we want to model side channels due to security-dependent, like say traces. This trace could come in from the timing, execution time, or could from the power or even EM radiation of the system when a victim is running, right? And we want to analyze the impact of this attack through real-world implementation. So our goal is to really understand the issues in real world. So we typically understand this by looking into real hardware and real systems. And then you eventually want to identify the root cause of this study information leakage attack and find good and efficient mitigation approaches. So in this project, I mean, I'm sure one demonstration we can show here is a recent work that we have basically figured out the new attack vulnerability in modern processor in branch predictors. So this basically, I'm not going to go into very detail about branch predictor design, but at a high level, branch predictor is a hardware unit that is incorporated in every single processor we have used nowadays. And then it's used to basically maintain the branch prediction information for branch instructions in the program. Our major observation is that when we execute branches speculatively, I mean, with speculation support, this kind of branch execution can change the status of the branch predictors, some data structures. And what's interesting is that we figure out that even if these branches instruction are later show to be under the wrong execution path and has to be scratched, the current processor, modern processor, still maintains the status changes due to the executions. Basically, doesn't scratch, that doesn't revert back that status change. And this actually can leave a potential new attack variant. But with this observation, we show the new attack, which is called branch Spectre. We think this is a new variant of Spectre attack that has been shown before since 2018, where it allows an attacker to exfiltrate secret information in the speculation domain by just abusing the branch predictor, or compared to the prior work that requires to populate a lot of microarchitecture component for this information leakage. Our identified attack is actually more dangerous in terms of using less attack hardware component. And also we find that there exists a lot more available and vulnerable gadget in today's victim programs, which make the attack surface even broader. So the right side shows our timing observations by only just looking at how branch is predicted in the attacks program. We can see that by observing the latency of a branch prediction, I mean, we can observe precisely what is the influence of a branch prediction that has been made by the victim's branch execution. And with that, we have shown that we can recover the secrets in today's commercial commercial open source applications that are security sensitive, such as OpenSSL. So we're able to recover secret with 100% accuracy with that for that applications. And we actually have a lot of other works looking at side channels from different aspects. Essentially, this project we will use side channel attack vector in modern processor, and we try to offer understanding about the security impact of discovered hardware-based threats, and eventually want to provide a practical defense solution that could be deployed in real systems with no cost to protect system against this attack. And we have multiple papers in terms of attacks and defense in this domain, and several papers under submission. And also we are having ongoing proposals, discussion, and planning along this line. And the last project I want to talk about is the understanding and taming deterministic model bit flip attack in deep neural network. So basically now we know that the hardware is not perfect. There are so many issues, weaknesses, vulnerability in the hardware. Then a natural question we want to ask is, what is the issue of hardware? What is the impact of this hardware vulnerability to some emerging applications that are truly critical, such as machine learning, right? We know that there has been a tremendous advance in machine learning in recent years, particularly DNN or deep learning has been deployed to many security sensitive applications such as image processing, voice recognition, autonomous driving, and natural language processing. So previously, the major security studies on machine learning focus on how the external threats, right, can tamper or can actually compromise a machine learning model. And examples of this includes as adversary input attack, which is under what I studied recently, basically shows that an attacker can add perturbations to input and try to compromise the integrity of the system. But what we figure out is that recently there are so many hardware-based vulnerabilities, and this hardware-based vulnerability, if exploited, can actually tamper internal of this machine learning model. And we know that this threat can be potentially even more dangerous because we know that the core of a machine learning, or let's say a DNN model, is the model parameters and model architectures. If those internal structures are tampered, it potentially can create even more damage as compared to the previous studied external threats. So in this project, basically we want to really, with observance of the rapid advance of hardware-based attacks such as fault attacks, want to understand what are the impact of this faults to machine learning model in terms of the robustness and what we can do to build robust ML models against such attack. And I believe that we are the first one to actually study the impact of the deterministic bit flip fault attacks into machine learning models. On the right side, I'm going to demonstrate two attacks that we have recently been investigating in the past 1 or 2 years. We're specifically looking at the DRAM fault attack, which is widely this fault that has been there for almost all commercial DRAM DIMMs nowadays. This is called a row-hammer fault attack, where essentially we have figured out by a group of researchers like probably 6-7 years ago, basically, it's possible that if you access certain DRAM, let's say bits or DRAM cells frequently enough, it's going to create sufficient crosstalk or electrical disturbance to labeling cells, and which may storing some other data from different applications. And this kind of crosstalk effect can eventually cause bit flip in memory without even accessing them, right? And it's extremely hard to actually detect or defend against this attack with no cost. And this is actually being an even more severe problem in recent years because of the technology scaling. You have using smaller cells, and cells are becoming much closer to each other. So what we do is that we understand if we have faults that could be triggered by this kind of hardware vulnerabilities, what is the impact to machine learning? So in a paper we have published in user security last year, what we figure out is that if we identify a specific algorithm to find the most vulnerable bit to fault in a machine learning model, actually the model could be very vulnerable to fault attacks. Example we have shown here is that let's say we have a classification applications using let's say DNN, actually convolutional neural network. As originally without the faults, we can achieve 90% accuracy, which is quite high. But after just injecting a few bit flips in this model, we can reduce degrade the performance or prediction from 90% to 10%, which is almost the same as random guess. So this observation is extremely, I mean, surprising for us because originally we think that machine learning models are very robust. For example, if you have some noise to images, is usually robust enough to identify this as the class, I mean, correct, let's say object or labels. But our observation is that those existing machine learning models are not designed to be robust against hardware-based bit flips, especially deterministic bit flips. And we need a sufficient amount of additional mechanism from either algorithm level or software to protect them. And the more recent work that we just published and presented actually last month is we studied the fault attack impact to modern natural language processing tasks. We specifically looking at neural machine translation model. And what we understand a specific question is that can fault attack influence the translation of a neural machine translation model? Let's say the origin we have a German language sequence, and without originally this could be correctly translated to one English sentence here. But by injecting force, we show that actually the attacker can control the output of this translation to a lateral sound, and attacker's control sequence, which is a
And you need to
different
wrap
sentence.
up. We are
Sure.
over time.
Okay. So and basically our observation from these two attacks is that I mean, existing ML models are not designed to be robust to these hardware-based vulnerabilities. And we basically call for future research in design secure and robust architectures for machine learning models. We have one, active grant under this and a couple of publications in this project. So with that, I want to quickly go over some future research and potential collaborations. In short-term research, our short-term research direction includes side channel attacks and defense in modern processors. We also want to look at looking at leakage-free, secure by design future architectures, tamper-aware architecture design for machine learning systems. So in the long term, what we want to do is to really have closed-loop secure computer system design that requires a secure mechanism across layers from software, compiler, operating system, architecture to all the way to hardware. We also want to look into reconfigurable and verifiable secure architecture. Basically, we want to have provable, have theory level proof that this is our design is secure. And then we want to look at a privacy preserving and tamper resistant accelerators and circuit design. In terms of potential collaborations, I think we need a lot of help from, let's say, formal verification expert, AI and NLP researchers, and domain-specific security expert for our security design in the future. With that, I would like to conclude my talk, and I want to thank our sponsors, my collaborators, and my PhD students.